Hello, ladies and gentlemen, and welcome to the last section of Topic 10 Notes. This is Topic 10C, Climatology. So it's going to be, hopefully fairly obviously, the study of climate. Now, a reminder from back in Topic 9 about the difference between weather and climate. Weather is the short-term conditions of the atmosphere at a given location, and climate is a long-term conditions. When we were talking about climate, I mentioned the absolute shortest period of time that we want to be looking at is a decade, 10 years. Really, we want to be looking at 50 to 100 years of change to see if our climate is changing. And when you start looking at trends over 100 years, then you can start seeing some good data going on. All right, so getting right into it, what is climate? So climate, again, unlike weather, is based upon atmospheric conditions measured over a long period of time, and it's for a region. So instead of just being for one specific city, you're looking at a continent, a state, a bigger chunk or area. So our atmospheric conditions would be things like temperature, precipitation, humidity, and things like that. The big things that we're going to be looking at is temperature and pressure. And that's actually how your climate is defined. So we are going to be using something known as a PEP ratio. So a ratio is one number compared to or divided by another number. So P stands for precipitation. So it's the amount of precipitation divided by EP, which is the possible amount of evaporation. That's actually just your temperature, because the warmer it is, the more evaporation you can have. The colder it is, the less evaporation you have. So when we're looking at our PEP ratio, it's the amount of precipitation divided by the amount of possible evaporation, which is related to temperature. So we have this little chart here that we're going to fill out that defines the PEP ratio, the climate, and then an example of it. So looking at this chart, and if you can, I do recommend that you color code it, just like I did, just to kind of give yourself some little helpful hints here. Our top box that we're looking at in our PEP ratio is a PEP of 1.2 or greater. That means that you have had way more precipitation than you do evaporation. So your numerator precipitation is much higher than your denominator. This would be a humid climate. So 1.2 or greater, you are humid. And examples would be rainforests or the jungle. So rainforests can be warm or cold. For example, there's rainforests in Alaska. There's also rainforests in Costa Rica. Then, if you are 0.8 to 1.1, and it's actually 1.199999999, so anything less than 1.2, you are subhumid. So this means your evaporation and your precipitation are about equal, give or take a little bit. Examples here would be temperate forests, and a hint for you, Allegheny limestone falls into this range. We're right about around 1.19-ish, and that is our PEP ratio. Then, if you have very little precipitation compared to evaporation, but you still got some going on, you are 0.4 to 0.7. You are semi-arid. You would be a grassland or a savanna. So most of the middle of the United States falls into this grassland, savannas like the Serengeti in Africa. Then if you have very little precipitation, or you're just so hot that the amount you have is nothing compared to the amount of evaporation you could have, well then you're 0.4 or less. You are arid, and these would be tundras or deserts. A reminder, the driest place on our planet, the most deserty desert, isn't actually somewhere hot. The most deserty desert is actually the Arctic and Antarctic. It's just so cold. There's no evaporation and thus no precipitation. Most other deserts fall at about 30 degrees north or south. So they tend to be at 30 degrees north or south, or around 90 degrees north or south. And the reason for that is our climate wind belt. So there are areas where there is very little moisture being pulled into the atmosphere. The wind belts tend to be descending, coming down. So instead of rising up and adiabatic cooling, they're descending. So this little information here is just kind of something to help you out with some of your reference table or your CASEL learning questions. Just something to keep in mind. It is also listed in your reference table on your wind belt page where it mentions dry versus humid areas. So again, make sure you copy this down. If you can color code it, awesome. If you can't, well, you did your best. Factors that affect climate. So these are things that are going to change your temperature or your precipitation. So the first thing we're going to talk about here is latitude. And this goes back to what we talked about with insolation, that because we are on a circle, different latitudes get different intensity of insolation, and that changes your temperature. So latitude, due to the angle of insolation, this determines local temperatures. And this should be pretty straightforward. Sorry, I dropped my pen. That regions near the equator tend to be hot. And again, the reason for that is that there is more direct sunlight. And then regions near the poles tend to be cold. And the reason for that is there is less direct sunlight. Ditto to what I wrote up there. So again, equator tends to be hot because there's more direct sunlight, the sun stays overhead. The poles, less direct sunlight, so it is cold. So here's just kind of a map showing you average temperatures, but it's also showing you how those temperatures kind of shift with the seasons a little bit. And a reminder that has to do with our angle towards or away from the sun as we're revolving around the sun. So our angle always points towards the North Star, but our position relative to the sun changes. You can see those belts warming and colding. Colding? That's not a word. Let's pretend it is. All right, our next factors that affect climate is altitude. A reminder, altitude is your height above sea level. And as we know, warm air rises, expands, causing it to cool. So high altitudes, high above sea level, have cooler climates due to that adiabatic cooling as you go to higher elevations. This is how we can have snow near the equator. If you have mountains near the equator and you're high up, it doesn't matter how much sunlight you're getting, that adiabatic cooling is going to force the air to cool. So again, mountains, this is why they keep their snow caps and stay nice and cold. This is why Allegheny stays cold a little bit longer than lower elevations near us. One of the reasons. It's our higher elevation. Right, mountain ranges. Besides just changing your elevation and changing your temperature, mountain ranges change precipitation and temperature patterns. They actually are causing deserts to form. So if you ever get bored and spend a long time looking at a map, every single desert is near a mountain range. Even the Sahara is actually geologically kind of near some mountains in our Middle East. So they're affecting them. And what happens is you have a windward side and a leeward side of your mountains. I'm going to pull these up to get all the definitions at once. So windward is where the wind comes from, and it tends to be near a body of water because water tends to stay cooler than the land, so high to low pressure. So as that wind is coming in, it's going to be cool and moist, making the climate cool and moist. Think Seattle, San Francisco. But then that cool, moist air is forced upwards. It forms clouds and precipitation. So on the windward side of the mountain, you get rain, and you can see this in that diagram down there. Then the leeward side is the side away from where the wind is coming from. So it's farther away from the body of water. So the air begins to descend, and it's warm and dry. It's already rained out all of its precipitation. So this is known as the orographic effect, or a rain shadow. So what we're going to write down for the orographic effect is that our wind comes in towards the mountain. It rises, expands, cools, and rains. So that gives us our windward side. That's cool and wet. Then it continues over the mountain. It descends. It compresses, and is dry. So we get deserts. Find a little cactus over here on one side of the mountain, and really lush, wet forests on the other side. And this is all because of the rain shadow or the orographic effect. So again, wind comes in towards the mountains. It rises, expands, cools, and rains. So you get your wet side on your windward side, wet, windward, wet, windward. And then it continues over the mountain. It descends, compresses, and heats, and is dry. So there's less on the leeward side, less on the leeward. It's hot and dry. So again, this is why we have deserts near mountain range. Windward, leeward. So here's just a little illustration showing this. Windward versus leeward side. Right, continuing on with our factors that affect climate. We have oceans and large bodies of water. So water has a high specific heat. It takes longer to heat up and cool down, which means land near it is going to have a more moderate climate. So if you are near a large body of water, you have a more moderate climate. That means your temperature ranges aren't as extreme. So you are cooler in the summer and warmer in the winter. So if we were to look at a graph showing us temperature over a year, and I wanted to look at something far away from water. Well, in the winter, it's going to be very cold, and then it's going to warm up in the summer, and then get cold again in our winter months. But if I was away from water, I'm going to have kind of a more average temperature. So again, this is close to water, you have an average temperature. This is far from water, you have a more extreme temperature in there. So continuing that, climates away have more extreme or greater seasonal variations. They have cold winters and hot summers. So here is a map of the United States showing this, and I'm showing everything kind of right along like 42 degrees north. So I have Fortuna in California, Omaha, Nebraska, Pittsburgh in Pennsylvania, and New York City. And what I have here is the average temperature. So Fortuna is an average temperature of 52 degrees. Omaha, 55 degrees, Pittsburgh, 54 degrees, New York City, 56 degrees. So they are all kind of around the same. Fortuna is a little colder, and we're going to talk about why. But then if we look at the extremes, Fortuna on the ocean, its coldest month average is 42, and its warmest is 63. That's not a big difference. Where Omaha in the middle of the United States, its coldest month average is 22, and hottest is 87. That's a huge, huge, huge difference there. New York City, again, kind of close to Fortuna, 36 versus 75, not as extreme of a variation. We're going to talk about the reason Fortuna actually is colder than New York City is Fortuna has a cold current coming down, whereas New York City has a warm current coming up. Now, we can actually look at this on a smaller scale by comparing Buffalo and Allegheny. Buffalo is right along Lake Erie. Its average cold in January is 34 degrees. Its average high in July is 75 degrees, whereas Allegheny, its average cold temperature in January is 30 and in July is 80. In fact, crazy fact, Buffalo has never had a temperature of 100 degrees or higher. The hottest recorded temperature in Buffalo, New York is 99 degrees. They've never made it higher, and that's because Lake Erie helps keep it cool. Whereas in Allegheny, I would say on average, we have 1 or 2 days a year that actually peak at like 101 or 102 degrees. Continuing on with our factors that affect climate, and this is something we were just talking about, ocean currents. So ocean currents are kind of streams or paths of water circling through ocean basins. They are driven and affected by the air above them, but they also change the temperature. So if you're near cool water or a cool current, it will cool your air. If you're near warm water or a warm current, it will warm your air. So this is why the west coast of the United States tends to be a little bit cooler than the east coast of the United States. We have a much colder current going by the west coast. We have a much warmer current going by the east coast. So page 4 of your Earth Science reference table has some specific names of currents and whether they're warm or cold. So for your Castle Learning assignment, I asked you, is this coast affected by warm or cold in South America, in Australia? What's the name of the current that warms this area? And that can be found on page 4 of your reference table. A reminder, you can find the reference tables on my webpage. Then planetary wind belts. These also are going to influence your local climates. Planetary wind belts are in your reference table closer to your weather stuff, around like page 11, I think. So these actually are what drive ocean currents and determine its effect on climate, and they're on page 14. I was close with 11, not really. So here's just kind of a quick thing showing our planetary wind belts from page 14 and a similar diagram to our ocean currents on page 4. And again, they are all influenced by each other. And they're also influenced by the Coriolis effect. So the fact that the Earth is spinning causes these wind belts to also spin. Now, more factors that affect climate. Monsoons. So monsoons are rainy weather brought on by large continents. So the fact that continents are where they are actually can change your weather, crazy enough. And basically your winters are cold and dry, so you have high pressure systems there, but your summers are warm and rainy. You have low pressure. So areas near coastlines like India actually have a rainy season where all their precipitation falls in a matter of weeks or just a month of time. Then typical storm tracks. As we mentioned in Unit 9, in the United States, our weather tends to come from the west and go towards the east. This is driven by our jet stream and our giant planetary wind belts. So again, in the US, we go from west to east. And these tracks are named according to their region of origin. So continuing on, here it's just kind of showing regions that tend to have monsoons. So we can see that they kind of fall all over our planet. Now, the next thing we're going to talk about is El Nino and La Nina. And they can be a little bit confusing. So El Nino is known as the warm water phase of the El Nino Southern Oscillation, or ENSO, cycle. So warm water oscillation. Basically, the eastern Pacific Ocean becomes weirdly warm, and this tends to happen once every 3 to 10 years normally. And because the ocean gets warm along that specific spot, you get all sorts of changes to your pressure, and pressure drives all weathers. You get typhoons and cyclones and flooding all over the place. You get droughts in areas like Indonesia, and it just makes things crazy. So this is kind of showing those effects of El Nino that you get. So some areas get warmer, some areas get wetter, some areas get drier. It's all about these change in pressures. So if El Nino is the warm water oscillation, then La Nina would be the cool water oscillation. And basically it makes the opposite global patterns of El Nino. So if you were going to be warm and wet, you're now cold and dry. And again, these tend to happen once every 3 to 10 years on average. But there has been a disproportionate amount of El Nino seasons because our ocean is just kind of warming up in general, and it's been making our weather go kind of wacky cuckoo crazy. This is just a quick video about El Nino and La Nina. Unfortunately, I can't seem to get it to play while recording my PowerPoint, so I am just going to post it on my webpage so that you can look at it on your own later. It really is a quick, short, little 2-minute video about the difference between El Nino and La Nina, and why it is called what it is called. So I would love it if you watched it. And again, I will post it on my webpage with the videos that are going along with this. That takes us into kind of our last thing here, water budget graphs. And I actually kind of drew an example of part of a water budget graph earlier. And this all goes back to our climate type chart that we did at the very beginning, 22 minutes and 27 seconds ago. So water budget graphs are the visual representation of the PEP ratios. So it's showing you the amount of precipitation versus the potential for evaporation. There are 2 separate lines drawn on there. So in here we have our blue line is the amount of precipitation, and our red line is the amount of possible evaporation. Keeping in mind that that directly relates to the temperature. So where you have a higher temperature, you have a higher evaporation potential. And that tends to happen in summer months. Lower temperature, you have a lower evaporation potential. So those are your winter months. Here we have a couple water budget graphs where we can see our climate types in here. Our first one is a temperate climate in the northern hemisphere. So our PEP number is probably somewhere around 1. The reason for that is we have a fairly steady amount of precipitation. We have months where we have very little evaporation, months where we have a lot of evaporation. So it's going to about equal out. So that gives us temperate. I know it's in the northern hemisphere because I'm warm around June, July, August, and I'm cold in January and December. Southern hemisphere would look like the opposite. Then my next one down, I have a PEP ratio. That's probably around like 0.2. So I have very little precipitation all year, and then I have higher amounts of evaporation potential all year. Again, this is the potential for evaporation because if the water's not there, you're not evaporating it. Again, this would be in the northern hemisphere because we're warmer in June, July, August, and colder in December. Then we have a couple more graphs here. Our next one is showing us a graph very, very similar to what we saw in our first graph, only now we're in the southern hemisphere. So again, our PEP ratio is probably somewhere around like 1.0, 1.1. So we have a steady amount of precipitation. We're warm in the summer and then cold in the winter. But this time, summer months are January, December, and winter months are June. A reminder, the southern hemisphere's seasons go in the opposite order of ours. And then finally, our last one would be somewhere like a rainforest, where our PEP ratio would be definitely 1.2 or higher, because our precipitation is constantly higher than our evaporation potential. And because we have very little variation in our evaporation potential or in our temperature, we are probably near the equator. Very little variation in temperature. All right, so that takes us to the end of this unit, the end of this PowerPoint. There is a CASEL learning assignment for this, and then next week you'll be working on a review assignment and your test. So thank you very much for joining me. Don't forget to go check out that El Niño La Niña video that I also posted on my webpage. Have a great day.